My name is Bertha Prince, the Energy Program Manager for Navista and CEMAI. I would like to welcome everyone to our second online energy training session on maximizing energy saving opportunities for community facilities. On behalf of Calista Corporation, I would like to thank Department of Energy, Indian Energy for funding the CEMAI program. All participants will be muted during the presentation. We will have about 15-20 minutes at the end of the presentation for question and answer. You can also type in your questions in the comments section, and then Tashina or I will read out your questions at the end. Since we have a small group of folks, we'll start off with introductions. Please state your name and where you're from. We'll begin with the folks on the phone. Is there anybody that's dialed in?
Hi, this is Sandra Hill calling from the city of Hooper Bay.
Good morning, Sandra. Welcome.
Good morning. Thank you. This is Sandra again. Sandra Hill from the city of Hooper Bay.
Is there anybody else on the phone? We'll move on to the people that joined through Zoom. We'll start off with Tashina.
Good morning, my name is Tashina Duttle, and I've been working with the CEMAI team for a few months now. I worked at ANTHC for a long time, so have a background in some of the stuff we'll be chatting about today, and just wanted to welcome everybody for joining us. Thank you.
We'll move on to Bailey.
Hi, thanks, Bertha. I'm Bailey Gamble. I'm an engineer with the Energy Department at ANTHC.
Thank you. Jim Fowler.
There we go. I'm unmuted. My name is Jim Fowler. I'm also an engineer. I'm focused pretty exclusively on energy efficiency in Alaska. Been doing this for about 10 years. So I'll be talking about efficiency today.
Thank you, Jim. Is there anybody else on?
Good morning. This is Sandra Tall Lake calling from the city of Hooper Bay. I'm the city of Hooper Bay's city administrator.
Hello,
Welcome,
my name is
Sandra.
Paula Hill with oh, hello.
Hello.
My name is Paula Hill with Native Village of Hooper Bay, tribal admin.
Welcome, Sandra and Paula. Is there anybody else that joined us?
Hi, this is Billy Rivers from Scammon Bay.
Good morning, Billy. Welcome.
Hello? Hello?
Hello?
Hi, this
Hello.
is Bernice Keene. Can you hear me?
Yes, we could hear you.
Oh, I'm Bernice Keene, and I'm from the city of Guijo.
Good morning, Bernice. Welcome.
Good morning.
Is there anybody else that I missed or joined?
Hello, can you hear me?
We
Hello,
can hear you.
this is Jackie Landlord.
Hello.
This is Jackie Landlord from the Azatesagu tribe in Mountain Village.
Welcome, Jackie.
Good morning.
Is there anybody else?
Morning, can you hear me?
To introduce themselves. Hello.
Good morning, could you hear?
Yes.
This is Josephine Nook calling from the city of Lower Cascade and city clerk.
Welcome. Okay, we'll go ahead and get started with our presentation. Today's agenda will be an overview of maximizing energy saving opportunities for community facilities. And then with the presentation by Jim Fowler. He's the principal founder of Energy Audits of Alaska. Jim will be discussing case studies from Yakutat, Kwethluk, and False Pass. And lastly, Bailey Gamble of ANTHC Rural Energy Initiative will be discussing energy efficiency in community buildings. And then a brief overview of the UAF Sustainable Energy Program. And then we'll list a few of our distance delivery energy training sessions this fall and spring. Okay, meet the CEMAI team. Christy Williams is the Government Relations Manager for Calista Corporation. Natalie Hansen is the Executive Director for Nuvista. And I'm Bertha Prince, Energy Program Manager for Nuvista and the CEMAI program. I'm originally from St. Mary's and have ties to the Lower Yukon. Our CEMAI partners and technical service providers are Brian Hirsch, Tim Leach, Devaney Plentovich, and Tashina Duttle. They're our energy experts of the program. The purpose of CEMAI, Calista Corporation received a grant from the Department of Energy, Indian Energy in 2016 to establish an intertribal energy providers network in the Yukon-Kuskokwim region. CEMAI's purpose is to reduce energy costs, improve operational efficiency, and assist our people with understanding the energy needs of the region. Our goal is to provide rural energy best practices, economies of scale, and improve operational efficiencies in the region. We assist the communities by creating an energy roadmap that integrates energy plans and energy priorities to strengthen the community going forward. Our program objectives identify community and sub-regional energy needs, provide access to funding or multi-level expertise to address existing challenges, develop specialized trainings like the distance delivery tracks that we're offering, nurture the creation of regional support networks, to increase access to regional, state, and federal and energy initiatives like funding, and lastly, align YK Delta energy and economic needs and reduce energy costs. At this time, I would like to welcome our first presenter, Jim Fowler. He's the principal owner of Energy Audits of Alaska. Jim is only an engineer in the state, focusing on energy efficiency. He's been working with tribes, municipalities, and other building owners across the state for about 10 years and has performed energy audits on more than 500 buildings. And for the last couple of years, he's been working with commercial fishermen to improve the energy efficiency of their vessels. Please welcome Jim. Take it away, Jim.
Thank you, Bertha. A correction there, I'm not the only engineer in the state. I think I'm the only one that focuses exclusively on energy efficiency. A lot of other engineers focus on energy efficiency. So what I'm going to be talking about today, if you want to flip to the next slide, Bertha, is okay, so it's a little different. Two case studies. One is of a small residence / commercial building, and the other is a program that I managed for the Yakutak School District. And then at the end, we're going to look at what's possible. And I guess Bernice is from Queethluck. We did a project there. Queethluck got a START grant a few years ago, and we did an analysis and tried to implement a community-wide program, but I think it failed for lack of funding. And then quickly look at a false pass, what's possible in a false pass project. First of all, if you want to flip to the next slide. This is a kind of an encapsulation of the energy efficiency process. It needs to start with a goal, as most projects do. And in this case, I just said, let's look at a 15% reduction of energy costs and energy consumption across a community. The next step is to take a look at what buildings do we have, and then establish what's called a benchmark or a baseline for those buildings. Look back a couple of years at the energy consumption for each building. And then that's part of what's called, what I call a portfolio analysis. Let's take a look at all the buildings in our portfolio and figure out which ones we're going to address first. That's part of the strategy development. The energy efficiency strategy answers the question of what's the plan. And then that strategy influences which buildings will receive energy audits. They may or may not all receive energy audits. But the audit answers the question of what is it costing and what are the low-hanging fruit? What's the low-hanging fruit in each of those buildings? Which buildings should we address? And then from there, once that is determined by the stakeholders, the building owners, then scopes of work need to be developed so that contractors can come in and estimate costs, or local resources can estimate costs. And then once you've got a hard fixed bids or hard costs for those scopes of work, then you're going to look at financing. I actually prefer that financing is looked at first based on rough estimates of costs, because if financing can't be achieved, it makes it real difficult to implement. After financing, the next step is construction and inspections. And then the piece that's generally missing is this called measurement and verification. A year after the program is complete, there should be an evaluation of answering the question of, did we save what was projected to be saved? And if the answer is no, then you need to dig into why, find out what's called the root cause for the less than expected savings, and fix it. Next slide. So in all energy reduction or energy efficiency plans, the black copy here, or the black text, is what needs to happen. The red text indicates some of the differences between a community-wide plan and a single building or a single building owner's plan. And down in the lower right-hand corner, that Alaska Housing logo that got dropped in there from an older presentation, this it's just ignore it. Doesn't have anything to do with this presentation. So basically the steps to create, to reach energy reduction is to create a plan and goals like we talked about in the previous slide. What's really important here is to appoint an energy champion. That's somebody in the community that will be paying attention to how much energy the building is consuming on a regular basis, at least monthly. And that person needs to be authorized to do something about it. If he or she is going from building to building, let's say you have 5 buildings, the energy champion should be walking through each of those buildings at least once a month after looking at the energy consumption of each of those buildings, making sure that the thermostat set points are correct, making sure that if there's toil stoves that are no longer programmed because of a power outage, they're reprogrammed, etc. You need to establish a baseline and monitor consumption. And then, like in the previous screen, portfolio analysis and energy audits. And in this case, for a community program, I always recommend that it's a community-wide analysis. Let's look at all buildings or all public buildings or all tribal buildings, ideally all buildings. The next step is to develop project development. And then for a community-wide program, funding sources and repayment mechanisms have to be identified. For a single building owner, that's less important because the building owner knows how much money he has and how much he's willing to put into that building. And then, as I mentioned, this measurement and verification needs to be implemented. And in a community, this typically requires ongoing service and training because my experience is in rural communities especially, there's a high turnover. So when the person who's monitoring the buildings leaves, another person needs to be trained to backfill that position. And the ongoing service piece of that is that, at least on an annual basis, these buildings should be evaluated and serviced, make sure the boilers are operating properly, make sure the thermostats are operating properly, etc. Next slide. So this is the first case study. This is a small 1,150 square foot single story building. It could be a home or it could be an office in a rural community. Basically, they're the same types of buildings. It's got a standard boiler. It's got baseboards. This one happens to be located in Anchorage. Anchorage has 9,500 what's called heating degree days. That's HDD, the abbreviation. What that means, an HDD or a heating degree day is essentially a measure of the severity of cold weather. To give you an example, Bethel, if Anchorage has an average of 9,500 heating degree days, which is, significant, but Bethel has 11,000. Utqiagvik has 18,000. Homer has 8,500. So the more severe cold, the higher the number of heating degree days, and that'll come into play in a minute here. So this building has 3 zones, manual thermostats, has a unit heater that runs wild. What that means is that the glycol or the heating fluid is running through the unit heater all the time. It has a constant volume circulation pump, which means that anytime there's a call for heat, the pump turns on. And it has a constant temperature boiler, which means that the temperature of the boiler is always at 180 degrees or whatever the set point is. The proposed conditions or the upgrade is to put programmable thermostats on 2 of those zones and set back the temperatures from 11 p.m. till 8 a.m. To 64 degrees. Put a zone valve on the unit heater so that the fluid is not flowing through there all the time. Put what's called a variable speed circulation pump in so that when there's a call for heat, if it's a small call, you can say the pump turns on very slowly. If it's a larger call, then the pump pumps fully. And then reset the boiler temperature based on the outside air. When it's really cold outside, you need a hotter boiler. When it's not very cold outside, you can turn the boiler temperature down. And then the other reset would be based on how much call for heat is there. Next slide. So this was actually implemented. The savings over the prior 2-year average was a 12% reduction in energy consumption, which equaled $745 a year at $5 a gallon for oil. I used a rural price for oil rather than Anchorage's price for oil. The total cost to implement this system was about $3,350. And again, I used rural numbers here, $1,000 for travel and $500 for labor. That's roughly 4 hours of labor to make the changes. The payback is the cost divided by the savings. So $3,350 divided by $745 a year. That means you get your money back in 4.5 years. Over on the right, you can see the 2017-18 and then the 2019-20. The red bar is the gallons of oil used, and the yellowish line up on top is the number of heating degree days. Between 2017 and 18, there was a reduction in oil consumption, but there was also a reduction in the number of heating degree days. You can see that it dropped from about 9,500 to about maybe 9,000. So that makes sense. The noteworthy thing, though, is that between 2018 and the 1920 year, the heating degree days went up, but the oil consumption went down. That's a result of the energy efficiency upgrade. Another way to look at that is the graph at the bottom. And that's when I took the number of BTUs, which is a unit of energy, converted the gallons of oil to BTUs, and divided it by the number of heating degree days. That kind of normalizes out the change in the weather. And you can see that there's a significant reduction between the 17-18 years and the 2019-20 year. One last point on this, the cost side here. You wouldn't typically fly a HVAC technician out to a rural community to do this one upgrade. So even though it may take 3 to 4 hours of labor, I threw in $1,000 travel cost. You would typically group, fly a technician out if you don't have a local resource, and have him or her do a number of upgrades to a number of buildings over a couple of days. So you'd amortize that travel cost out, and the payback would actually be less than 4.5 years. You want to flip to the next slide, Bertha? So the second case study is, well, that got a little bit messed up over on the side there, is a energy efficiency upgrade in the community of Yakutat. Yakutat received a $300,000 VEAP grant back in, I think it was 2013. And I was hired as the project developer and the energy auditor. At the end of the program, or the 3-year process, 2013, 14, and 15, they ended up spending $1.25 million on energy upgrades. And the pie chart off to the left, it's a little bit kind of disturbed, but you can see what the distribution of the funding was. About 85% of the money was spent on construction, which is great. That's the way it should be. The energy audits, project, and construction management was 80,000, which is about what, 9%, 8%, and the engineering was 6%. So to me, that's a good distribution of funds, given that most of it is being spent on actual construction. The unique aspects of this project, there were 2 schools. The elementary school is the building on the upper left. The high school is the building on the upper right. The city offices is lower right. Both schools were served by a heat recovery system from the power plant. The heat recovery system was 20 to 30 years old. There was no backup heat in either of those buildings. So if the heat recovery system failed, the buildings have no heat. That's a problem. The high school was at the end of the waste heat loop, or the heat recovery loop. So on the coldest days, there was insufficient heat there. There just wasn't enough heat being generated. There was 2 decades of deferred maintenance in the schools. So that the project really turned into more of a retro commissioning program, in that once we got into it, there were a lot of fixes made to the systems that were not functioning properly. You want to flip to the next slide? So this is the project scope. Before I go into that, the picture, the graph in lower right corner there, this is just one of the data logging graphs that I created from the during the energy audit phase. The gray line on the graph shows the temperature in the elementary school, the second floor of the elementary school. And the orange line shows the carbon dioxide concentration. That red line going across just under 800, that's supposed to be at 800, but it got moved a little bit. That's the recommended highest level of carbon dioxide in a building. One of the issues with these buildings was the ventilation wasn't working properly, so I wanted to see what the air quality was. And you can see that it routinely during the day exceeded the recommended 800 parts per million. You can also see that the temperature varied at night from about 74.5 degrees during the day to 78 degrees. And I didn't point it out, but the prior picture of the elementary school was taken in January, and you can see many, many open windows. The building was overheated, and so the occupants were opening windows routinely, and that's a huge energy sucker. Anyway, so the city owns these buildings. So the first step was to get stakeholders involved, community stakeholders. We did that with the city manager, the tribal administrator, the school board, the principal, and the maintenance person. We did level 2 energy audits on the 4 buildings. Then we found that we had to add in the waste heat system and another building that was on it, the public safety office. We data logged, we evaluated all the HVAC components. After the audits, we met again with the stakeholders and prioritized what they wanted done, and then had to get board approval, school board approval. After that, we had to do a pre-construction hazardous material inspection, make sure that what we were intending was not going to create hazardous material situation. I managed the construction through this. We did final inspections, and then we did a measurement and verification after 6 months. Next slide. The summary, the upgrades are summarized over on the left side there. The right side summarizes where the funding came from. There was a lighting upgrade done on the 2 school buildings prior to my arrival there. They used TURF funds, which is the Tongass Economic Relief Funds. I think that was from the Exxon Valdez monies. The $300,000 VEAP grant was matched with another $311,000 of TURF funds by the city. That was the project, the kind of the main meat of the project. And then the pool building was in really bad shape, but it was eliminated from the original, my portion of the project until afterwards, when a Rasmussen grant was obtained for $350,000 to upgrade and correct the problems in the school, the natatorium, which is the pool building. So total is at $1.25 million over 3 years. Next slide. This is just kind of a snapshot of some of the things that we found wrong with the school. The controls were pneumatic. There was severe overheating during most of the year. Windows were open, as I mentioned. The pneumatic compressor was running almost continually. All the air handling units, the fans were running backwards. And that was because some electrician came in at some point and switched phases in the main line into the school, main electrical supply. And so all the fans were running backwards. The kitchen makeup air unit was disabled. So every time the exhaust fans were turned on in the kitchen, they're blowing all the heated air out of the building. And significantly, the domestic hot water was running into the lavatories, the toilets and the lavatory sinks because of a failed check valve. So we had hot water in the toilets, and we had hot water on the cold water side and the hot water side of the sinks in the building. So that's just a snapshot of what was wrong. The next slide is a summary of the projected costs and savings. You want to flip to the next one, Bertha? By building on the left, the basic costs here were $5.26 a gallon for fuel. And because they were using recovered heat, we had to do an equivalency as if they were spending the money on oil rather than recovered heat from the power plant. And they were paying about 46 cents a kilowatt hour. So the implementation cost was $611,000. That was their budget. Savings were $131,000, and the payback was just under 5 years. If you flip to the next slide, this shows after 6 months, we had partial data for the schools. We did not have data for the courthouse and city offices, but you can see that the actual savings came in slightly below the projected savings for the lighting portion of the project. For the HVAC, or the heating, ventilation, air conditioning, and the electric and oil portion of the project, the savings came in a little bit higher than the projected. The reason that the lighting savings came in a little bit low is because the lighting contractor did not consider what's called a heating penalty. When you reduce the amount of wattage produced by lighting in a building, you increase the need for heat during the heating season. So then let's go to the next slide. This is the Queefluck project. This Queefluck a few years ago received a grant through the Department of Energy START program, Strategic Technical Response Team. I can't remember the acronym exactly, but I was there with folks from NREL, and we looked at, well, what if we took the 4 kind of low-hanging fruits in every building in the village, what would the savings be and what would the cost be for every resident and for every commercial building? And the proposed program over there on the right, these are the kind of what I call the low-hanging fruit. We said, what if we had setback thermostats in every building? What if we air sealed every building? What if we replaced all the lighting with LEDs? And what if we boosted up the attic insulation to an R60? What would the cost be and what would the savings be? If you want to flip to the next slide, the community-wide savings was just under 13%. On the residential side, the average homeowner was going to save $515 a year. It was going to cost $2,000 to make the upgrade, so they had a 4-year payback. And on the non-residential side, I think there were about 180 residences and about 26 non-residential buildings. The average savings was about $3,800 a year. The average cost was $15,000. So the payback was, again, about 4 years. So the community-wide, it was going to cost just under $750,000 to implement this. And there would have been savings, 96, about $200,000 a year in savings. Unfortunately, it did not get implemented because we couldn't, or I actually wasn't involved in the phase to secure funding, but I think Bertha and Tashina might have been. So the next slide summarizes the False Start got what's called a Kickstarter grant from AHFC to develop a project for their for 5 city buildings. So I was the contractor for that. Their biggest issue was that 3 of the buildings, the siding and the envelope was extremely deteriorated. False Pass has a really harsh environment for salt spray and wind and rain. We developed a project for them that met their needs. The total cost of the project was going to be $143,000 with about a $10,000 a year savings. I looked at 4 different financing mechanisms here and over a 15-year period. And this is the cumulative cash flow. So if you save $10,000 the first year, The second year you will have saved 20,000. The third year you will have saved 30,000, etc. At the end of 15 years, the most money in your pocket is going to be this grant in year 4 with a 50% match. If you take that program, you're going to end up with $44,000 in your pocket at the end of 15 years. If you do nothing, you're going to end up spending $149,000. So there's almost a $200,000 difference there between doing nothing and getting a grant in year 4 with a 50% match. On the other hand, if you self-finance, that's the gray colored. At the end of 15 years, you end up with $6,200 in your pocket versus do nothing, $150,000 outlay. So there's a $160,000 difference there. And Falls Pass actually did have the resources to finance it themselves, but they didn't. Then the fourth option was to take a loan out for 80% of the project cost at 3.8%. So you have to put out $30,000 in cash. That's the red set of bars. At the end of 15 years, you're down $31,000, but you're still $110,000 ahead of doing nothing. So this shows the value of doing something, and there's 3 or 4 different mechanisms there. So that's the my slide. If you want to go to the next slide, there's my contact information. If you want any more information on any of this stuff, please feel free to contact me. I appreciate your time. I don't know how I did for time. Thank you.
Well, thank you, Jim, for your presentation. It's always a lot of useful information. We'll save questions for the end of our presentation. I'd like to welcome our last presenter, Bailey Gamble, Mechanical Engineer for ANTHC's Rural Energy Program. Welcome, Bailey.
Thank you. All right. Yeah, thanks for that presentation, or thanks for that introduction, Bertha, and presentation, Jim. I really appreciate that last slide comparing the different funding options. So yeah, I'm a mechanical engineer with the energy department at ANTHC. ANTHC's vision is that Alaska Native people are the healthiest people on Earth, and our department works towards that vision by reducing the operational cost of water and sanitation systems, by reducing the energy costs associated, and hopefully that makes those systems more sustainable and more accessible for all. And so I'm going to talk today about energy efficiency in water and sanitation facilities, but a lot of what I'll talk about also applies to other community buildings. Next slide, please. Okay, so why are water and sanitation facilities ideal candidates for energy efficiency? And kind of going back to Jim's presentation there and looking at that portfolio, if you want to do an energy audit, and your resources are limited, a lot of times the water and sanitation facility or other large facilities like schools are good places to start because there's a lot of opportunity to save. They're big systems. They've often been around for a while, so they can be pretty old, and they have a high demand for energy. And one thing that's great about working with energy use in water and sanitation is that the savings associated with saving on energy can be passed to all of the members of the community in the form of keeping the water and sewer bill at a manageable amount to still sustain the system, and in some cases even reducing those bills. So why do water and sanitation facilities have such a high demand for energy? What makes them different? They have really high heating loads, above average heating loads, because a lot of times they're bigger, more space, needs more heating. They're often old buildings, so losing some heat through deteriorating door seals, sometimes broken windows. There may be even some cracking in walls due to differential settlement. If there's a washateria tied into the water and sanitation facility, then there's a demand for heat for the water for washing clothes, domestic water just for sinks and showers, heat for drying clothes. And one of the biggest heat loads in the water and sanitation system is that heat needed just to prevent the water from freezing. So heat is often added, as you can see in this graphic here, heat is added at many different locations throughout the journey of that water from the source to the sewage lagoon. Heat often has to be added to the raw water to keep it from freezing during transmission to the water treatment plant, and so that it can reach the optimal temperature for the chemical part of the treatment process. Heat would be added again before that water is sent for storage at the water storage tank so it doesn't freeze in there. Heat is added again before water is sent out for distribution. So lots of demand for heat that can really add up. And they also have often above average electrical loads. There's often a lot of lighting if it's older, incandescent or older fluorescent, high pressure sodium type bulbs that can demand a lot of electricity. A lot of pumping, a lot of fluid is being moved, distributing water, distributing hydronic fluid to meet heat loads, circulating, moving that water so that it doesn't freeze as well. And just regular appliances. Old coffee makers can use a lot of electricity. And one tricky culprit is heat tapes. Heat tapes are tricky because a lot of times they're in locations where we don't see them, and we may not be aware of whether or not they're on. And a lot of times they're operating when they don't need to be. So all of these things add to that, those above average electric loads for water and sanitation facilities. Next slide, please. Our department has been working with operators across the state for the past decade on auditing water and sanitation facilities, and in most cases implementing some of the most economically beneficial energy efficiency retrofits. And so this slide is just a very general example of what some of those most common energy efficiency measures that we've been implementing have been. So just breaking it down, how do we help water and sanitation facilities to reduce their electric demand, to use less electricity? And those same low-hanging fruit that Jim mentioned in his presentation. We often will replace old light bulbs with new, more energy efficient LED bulbs. And a lot of electricity can be saved just by changing the way that components are controlled. Optimizing controls to operate components only when needed. And some examples of that would be rather than pumping and circulating water in distribution loops all year, only circulate it during the heating season. Or rather than letting a heat tape run all winter, automate it to operate only below a certain temperature threshold, or only when water is not moving in a particular line. So sometimes even without having to change components, we can make a big difference by changing how things are controlled. And then just replacing older components with new, more energy efficiency versions. So for example, pumps, pump efficiency and technology has evolved, as well as the way that we're controlling pumps. So like Jim talked about, rather than having a pump operate at a constant speed all the time, have that pump operate at different speed, depending on the demand for heat or whatever, and operate only when there is that call for heat. How can we help these facilities to demand and use less heat? One of those low-hanging fruits again, the temperature setback. Just turn the heat down when no one's in the building and that heat isn't needed for people's comfort. Weatherize to reduce the heat lost through the envelope of the building, and add only as much heat to the water as needed. So engineers would generally agree that maintaining the water in the range of 36 to 40 degrees is enough to prevent it from freezing in the lines. But sometimes we'll see that water is being heated to 55 or 60 degrees. and that may protect it from heating, or from freezing, but that's more heat than necessary, and that's burning a lot of fuel that doesn't really need to be burned. So just finding that sweet spot for what temperatures and how controls are set can help us to minimize the amount of heat that we're using in those facilities. We can also produce and transfer heat more efficiently by cleaning and servicing boilers regularly. Then we're ensuring that the most heat from that combustion chamber as possible is being transferred into that hydronic system and distributed to meet heating loads. And then we can also start to think about how we can incorporate other sources of heat other than just burning fuel oil in boilers and furnaces. A common system that you'll see in rural Alaska communities is taking that heat that is generated by diesel engines in the power plant and delivering that through hydronic pipelines to meet part of that load or all of that load at the water treatment plant or like the school in Yakutat. And this is veering into the renewables, so I won't go into this too much, but there are also systems that take excess electricity generated by wind turbines or hydroelectric turbines and apply that excess electricity to generate heat through electric heaters. So bringing in other sources of heat. Next slide, please. Okay, and so just a kind of a summary of work done in TVAC. I think that in the previous CEMAI panel, Dustin had talked about TVAC as an example. TVAC was one of the communities that we worked with on energy auditing back in 2012, 2013, and audits were conducted on the water treatment plant and vacuum plant. Those buildings were then modeled using the software program, and different retrofits or changes that could be made were evaluated to see which ones offered the most economic benefit. And so some of these smaller retrofits are just examples of retrofits that were, or changes that were found to make sense for those buildings through those energy audits. And so that work included reducing circulation to 9 months per year. So running those pumps that circulate water in the distribution loops only during that heating season, because before they were running all year round, and that wasn't necessary. And that was using electricity that didn't need to be used. Reduce raw water heating. So again, like dialing in that temperature to which water is heated and not heating it more than it needs to be to prevent freezing. Automate heat tape operations. So heat tapes are only operating when water is like stagnant in a pipeline or when certain temperatures are reached. Replacing LEDs in the treatment plant and vacuum plant, and recommissioning controls. And then there's examples of annual savings for making these different changes. There are also a number of larger projects carried out on the TVAC water and sanitation system. So I should mention that this particular system, it's an above ground pipeline. The terrain sometimes does not allow for buried pipes, and it's a vacuum sewer system, meaning that the terrain in TVAC didn't have the slope necessary for sewer to flow due to gravity. So vacuum pumps are needed to kind of suck that sewage and keep it moving in the pipeline. So this is a large-ish community with in a more energy intensive system than average too. Those above ground pipelines are going to be exposed and need to be insulated against the outside air temperatures rather than the ground temperatures. So during the winter, that air can often be a lot colder than the ground. So there's a lot of opportunity for savings in this particular system. Some of the larger energy efficiency retrofits were involved installing new, more efficient vacuum pumps, replacing old oversized boilers with more appropriately sized and more energy efficient newer ones. In 2015, a wind to heat boiler was installed that took the excess electricity from the wind turbines to an electric boiler in the water treatment plant. And to be honest, that particular system has it's had a lot of obstacles to optimal performance, and is still we're still working on troubleshooting that one, primarily because the turbines, it's rare that all turbines are up and running and operating at their full capacity, but that still has been able to offset fuel in the water treatment plant. And this year, we're finishing up construction of a heat recovery system that will bring that heat that would otherwise just be rejected to the atmosphere at the power plant over to the water treatment plant and vacuum plant to offset further fuel. Next slide. So that's what we've got. It's just a very introductory for the sake of time. This is my contact here. So if you have any questions about energy efficiency work in water and sanitation facilities, and specifically want to know what buildings in your community that have been audited, or if you have the audits that are available online, I can guide you to those. They're on our website. I'm curious about what retrofits have been implemented from those audits. Please feel free to reach out and we can talk specifically about energy efficiency work that has or hasn't yet been done for water and sanitation facilities in your communities. All right, thank you.
Thank you so much, Bailey. This is a good segue into the Sustainable Energy Occupational Endorsement Program through the UAF Bristol Bay campus. It's a mini course the Bristol Bay is offering. They have tuition assistance available to interested participants. You could contact Mark Misteller with the UAF Bristol Bay campus. I've taken this course. It's quick. If you've done all your core courses, you could go through this certification program quite easily. And moving on to our upcoming energy training sessions that we're offering this fall and winter. You could register online at the address below, which is CEMAI.calistacorp.com. Click on the calendar tab. And we'd like to thank you all, our attendees, for joining us during our community facilities presentation. And we'd like to thank our presenters, Jim Fowler and Bailey Gamble, for sharing your knowledge with us. We'd like to thank Department of Energy, Indian Energy for the CEMAI program, Calista Corporation, Nuvista, ANTHC, AHFC, CCHRC, and Deerstone Consulting, and to our project partners, Tashina and Tim Leach, who's joined us within the last 15 minutes. Thanks, Tim, for helping put together this presentation. We'll open up the last few minutes for question and answer. Please state your name and where you're from so we'll know who's speaking. Any questions for Jim Fowler or Bailey? We have about 10 minutes, so if any of you have questions, or the floor is open. Tim, thank you for joining us.
You're most welcome. My apologies, I couldn't join you earlier.
Bertha, do you want to maybe mention like how folks could reach out to CEMAI to request technical assistance, and then maybe Bailey could talk about the DOE OIE TA opportunities over at ANTHC?
Sure, my contact information is below. You could email me if you have any questions. It's energy@navistacoop.org. I'll be happy to forward your questions to Bailey or Jim or our project partners.
And as Tashina mentioned, were you done, Bertha?
Yeah.
Okay, I was just going to mention our technical assistance opportunities. So there is a technical assistance request form on the Department of Energy Office of Indian Energy website. And it's a really simple form. I'm trying to see if I just Google DOE Office of Indian Energy. Yeah, if you Google Department or DOE Office of Indian Energy, right up in the upper bar there's a technical assistance link. And through that page, you can click on a form to apply for technical assistance. It'll just pop up a really simple email form that'll go to DOE, and through that avenue, if that is a technical assistance request related to energy that ties into water and sanitation in any way, and in some cases, energy planning and work that expands beyond water and sanitation as well. If you request technical assistance through that avenue, Alaska requests will often come to ANTHC if that's something that falls within our scope of our areas of expertise. And sometimes we will also work with subcontractors on these kind of projects. But it's a great opportunity that's open to all tribal communities and regional village organizations, corporations as well. A great opportunity to apply for technical assistance related to energy.
Thanks, Bailey. Bertha.
Thank you, Bailey. Well, thank you everyone for joining us. Like I said, if you have any questions, please email us. We look forward to seeing you at our upcoming fall and winter presentation by Zoom. Thank you everyone, and have a good day. Bye.
Thank you, bye.
Bertha.